Alright class, let's pick up where we left off with chunks and how they're allocated on the heap, and we'll dive into the free process. However, I want to cover a cautionary tale. Um, in lecture 1, I warned about the legal consequences of hacking and using it illegally. Um, And I explained that in some cases it can be punished worse than rape. Well, in this case, this is an example of how it's getting punished worse than, in fact, gang rape. Um, the picture of this gentleman is the, the man who hacked the Steubenville rapists and released a video that they recorded of them, well, doing a terrible thing to a young woman, and then they used that to humiliate the woman. And the video identified all the culprits involved, and he released it. However, he was rounded up by the police, and now he is getting more jail time than the rapists themselves. Now, say with that what you will, that's just my cautionary tale about the system. So, we discuss how chunks are allocated and how these pointers are redirected. And it is important to keep in mind that the system trusts that this data is intact. It trusts the integrity of this data. And so free is basically the reverse of this process. And it involves also changing pointers. And it's important to note that freeing a chunk twice will mess up these lists. And also it's important to cover this because the majority of buffer overflows since 2000 have been on the heap. And it's one of those aspects of C that developers just don't understand as well as other aspects. So let's use this totally sane and not racist guy to explain heap vulnerabilities. He really likes frees and he really likes heaps. So let's cover this basic code. It mallocs 3 objects. One is size 666, one is size 12, and the other one is size 12. And does a stir copy, and there may be some code in between, and then it frees them all. Alright? So as we discussed earlier, the issue of data alignment was really important in the past. And in one area that is survived is the heap. And that you will find that despite this mallocing 666, it's going to have to land on an even address, and it's going to have a size to accompany not just the 666 bytes here, but the metadata that coordinates the heap algorithms for allocation and freeing. So, what you will find is that after these are allocated, the stir copy is going to write data here. And it's going to write down in this direction because this direction is towards higher memory. And the algorithm for free is roughly, it checks if the next one, say we're doing free first, it checks if the next one is not in use. If the next one is not in use and therefore is also free, it attempts to consolidate the 2 chunks together and then merge with an existing chunk on the free list or that existing one. Otherwise, if the next one is in use, well, it just goes ahead and links this first chunk to the free list. So let's iterate through this example with this rough algorithm. So first it's going to check to see if the next chunk, this one, is also free. So what it's going to do is it's going to check the previous in use flag, not on the next one, but on the next one. So in this case, the next one says the previous one is in use. So the first one is just freed up. The previous in use on the next one is set to 0, and this one is then linked to the free list. So, iterating through this, it checks to see if the next one is also free, since we're doing free second now. Now, the next one is not shown, but in this case, this one is in use, and so the second one is just freed up and linked to the free list. And then the p flag on the next one, this being the third one, is set to 0. And so on and so on. Now, consolidation may happen in different settings. It depends on the allocator and the algorithms that it contains. And consolidation in these examples were not shown. But it's important to remember that consolidation calls that unlink macro that we discussed earlier in the previous lecture. So what's to note here is that pointers are changed in the chunk freed and in other chunks, and this relies on the metadata being correct. So if we want to explore how this is used maliciously, this would be the target metadata. But given that data writes towards higher memory, and that stir copy starts here, we can't write backwards, not arbitrarily in just this scenario. So in this example, we would only be able to hit the second size tag here. And so going over it again, we allocate all the chunks and we buffer overflow. And you'll see that this will alter the behavior of free, as it won't be able to use these flags and find out where the other things are, and it will likely cause the program to segfault because we've overwritten that important metadata that is used by those algorithms. So what if we do it smarter? This is a good example illustrating how to hijack the unlink algorithm and triggering the free algorithm to consolidate, which thus in turn triggers the unlinking. So from the beginning, by inserting a string just up to the point where you start overwriting the tag data, but then also include malicious data here, all the way up to this last malicious back pointer, let's explore how this example plays out in terms of an exploit. So what we're going to have is that this field, see how it's set to -4? When free gets called, it checks the next chunk. And I'm going to go backwards so you can see where the mouse is. That this is the size tag for the second chunk. And here's the p flag for it. And the clever thing that's being done here is that we're having another tag right before this. And what this is for is that we're telling the algorithm that the next chunk is actually behind us. This is just to make the exploit compact. And so it's going to check the next and then go back next chunk to see if the second one is in use. And we're telling it that it's free. And so when free goes here, it's going to find this and it's going to start the unlink algorithm. And what's going to happen, if you remember, is that we're going to set the forward pointer. P is set, right? BK and FD are not set. We're going to set FD and we're going to set BK to these malicious inputs. And it's important to note that these need not point to the heap or the free list. And then when this third command runs, remember the previous lecture, how this is effectively equivalent to dereferencing FD and then adding some offset to access a value of that structure. Let's just say it happens to be +8 or so. So it's going to go to FD, what we've provided here, +8, access that value of the structure, and it's going to set that address, that destination, equal to this value that we've provided. So to recap, we have a destination pointer that we're tricking this unlink algorithm to overwrite a value added with a value that we are providing. And it just happens to be an offset that's determined by the architecture, whether it's 32-bit or 64-bit, and the allocator algorithm. And those can be easily determined for a system. So this allows you to overwrite for a 32-bit system an arbitrary 32-bit value, a 64-bit system an arbitrary 64-bit value. And when we get into exploitation lectures and discussing security and how to protect against these things, we'll show how this can be used to enable exploits and to enable attacks, and why this is very important to consider. So the double free vulnerability condition is growingly more and more rare. It effectively involves freeing a chunk and then freeing it again, and it comes back to basically mess up the heap and produces some more or less kind of zombie state of the former heap, but it doesn't really cannibalize other chunks or bins doing so. But in order for this to be a vulnerability, the chunk that's freed must be isolated. In other words, there must be no free chunks adjacent to it, and that the free list that is getting linked to must also be empty. In other words, everything in that bin list must be used. Unfortunately, this is much more complicated than the last bug case, and we don't have time for it, but if you really want to dive into it, the Secured Coding in C and C++ by Robert Secord has a great discussion of it. And this vulnerability class affects DLMalloc and old versions of RTL heap. But most modern allocators do some form of safe unlinking that prevents many of these cases. However, a hard to protect against case of bugs that often can be vulnerabilities is use after freeze. And basically, it involves using something on the heap that's already been freed in some fashion, whether it's being used in the logic to control execution or being used as a function pointer. If an attacker can control that data after it's been freed and then it's getting used again, an attacker can subvert the process and hijack execution potentially. So that ends that section, and we're going to pick up with integer security and also cover floats at the end of it. But we're going to start covering signed versus unsigned integers, cover integer truncation, cover overflows, underflows, some nuances, conversions and promotions and casting. This is illustrating for chars, which are just 1 byte, what the bit values are for various settings. So on the left are signed values, and those follow the 2's complement. And if you're not familiar with the 2's complement, you should really brush up. It's rather important to know. And so for negative values, the signed bit, the most significant bit, is set. And for the max value, I should rather say, the minimum minimum assigned value, here being -128, is going to have the most significant bit set, and the rest being zeros. And the largest negative value, being -1, is going to have all the bits set to 1. And conversely, for unsigned values, when they're all set to 1, in a byte is going to be 255, and when they're all set to 0, it's going to be 0. So this, going back to this, for 32-bit integers, -1 is going to still be all ones, and for 64-bit integers, it's going to still be all ones. And it depends on the architecture, of course. So this is an integer truncation example, how we take an integer I and set it equal to -1. An integer is signed by default. And then we're going to take a short x and we're going to store I into x. And we're going to see how this plays out. So we have the function prolog, and what's being set up here is that it's moving -1 onto the stack and doing the calculation, well, doing the move right here, and then moving the result into the value on the stack that is reserved for x. Now you'll see that it's moving AX instead of EAX. So AX is only the first 16 bits. EAX is the first 32 bits. So it's chopping off half of that value. So that's an example of how truncation can cause information to be lost. And if that plays a role in a program's logic, it can cause bugs, and maybe it can also cause vulnerabilities. And while we're at it, if I haven't discussed it already, the difference between 64-bit registers and 32-bit registers is that 64-bit offers many more registers for general purpose and extends the 32-bit general purpose and other registers by a R modifier replacing the E modifier. And R simply just means the 64-bit extension of that. And so EAX will still address the lower 32 bits. AX will still address the lower 16. AL or BL or CL or DL will address the lower 8 bits of that register, and so on. Then let's cover integer overflows. So this is a pretty good example of what happens in a unsigned setting. The C99 standard dictates that the result is always modulo, that any computation involving unsigned operands can never overflow. And so effectively what happens when you get to the max value and add 1 is going to wrap around to zeros. And so hence uint max plus 1 on any compiler should evaluate when executed to 0. However, what about signed operands? It actually turns out that overflowing a signed integer is undefined behavior, and that taking int max plus 1 is actually undefined behavior. However, in some other settings that may not adhere to the C99 or other C standards, you may observe a phenomenon called result saturation. And this occurs in graphics processing units and digital signal processors and other equipment. And effectively, wraparound does not occur. Instead, a max value is always returned, and you'll never see it wrap around from max value to zeros. And it's important to note it does not overflow into adjacent memory. It just sits at that max value until it's decremented by some amount. Which leads us to underflow, which can only occur in subtraction. And so unsigned int x, 0 minus 1, is effectively the same as 2 to the 16 minus 1. And the C99 standard dictates that the result is always modulo for unsigned operations, and it will wrap around even in subtraction. However, for signed operands, this is again undefined. So int min minus 1, and accordingly, negative int min results in undefined behaviors, oddly enough. There are other nuances that we should cover, that negative integers cannot be left shifted. For instance, -1 left shift by x is, for any value of x, is undefined behavior. It is also an error to shift a 1 into the sign position. For instance, that would be done by int max which would be 0, 1, 1, 1, 1, 1, 1, 1 for however long that goes. And shifting it left by 1 is actually also undefined behavior according to the standard. However, some compilers will allow it. And it is also an error to shift the value by more than the bit width of that object. For instance, a char is a byte. It's actually an error to shift it by more than 8 bits. It's an error to shift it by 9 bits. For a 32-bit integer, it's an error to shift it by 33, and so on and so on. There's another class to consider, that when you compare unsigned values to signed values, the compiler engages in something called integer promotion. It promotes the signed operand to an unsigned operand for the purposes of carrying out that operation. For almost all operations, as far as I know. This is a very good link that explains many of the integer conversion rules, and I recommend reading it. It should come in handy for the homework. And so effectively, comparing unsigned 1, if you didn't have the U here, it'd be signed by default, so it'd be signed versus signed. So unsigned value of 1 compared to signed value of -1 gets promoted to unsigned integer max. So that will evaluate to false, actually, which is interesting. So that can, as you see, perhaps lead to some bugs, depending on the setting. And also, for size promotion, operands usually get promoted up to size int. For instance, if a number type is smaller than int, when an operation is performed on it, it usually gets promoted up to int for the purpose of that operation. So actually, remember how we said it is an error to shift something by more than the bit width of it. This operation actually promotes x up to an int, which is going to be at least 32 bits on most architectures, if not 64 bits. Perform this and then do the typecast in the end, which is actually still valid. So here are some other cases to consider. The first line, x minus 1 plus 1 and then typecast as an int, is actually undefined if x is int min, because this first operation is going to cause a problem if this is int min and then you subtract it, as underflows are not allowed, and this will cause an underflow despite this being -1 and then +1. Before it even gets to the +1, that error will have occurred. And that obviously depends on how the program, that line of code gets compiled. Perhaps your compiler will see, oh, you have -1 plus 1. Oh, that's really the same as +0, which is, we really don't have to do anything. Or it may optimize that out, and in realizing that, just not do anything for that line of code. Another setting to consider, int min modulo -1 is quite interesting. Modulo a negative number is, I believe, undefined behavior, and taking this, which would be even more interesting twist on undefined behavior, may yield very interesting results. Lastly, this example, short x plus 1, does it always equal short of parentheses x plus 1 for all values? So if x is a signed int and it is signed int max plus 1, that's going to actually be a overflow of a signed integer, which, as we discussed, is undefined behavior. And it won't evaluate the same as this, I believe. So As far as integer casting, if you take a negative value and cast it as unsigned, and for instance, if you take -1 and you cast it as unsigned, it's going to become unsigned integer max, or, well, this slide is copy and pasted, so it's not going to become 255. I forget off the top of my head, 655 something for 32-bit. And so there are two data types or primitives that are important to consider in discussing size and calculating size. The most common one is size underscore t. And the C standard dictates this is an unsigned int, and the reasoning is that sizes should never be negative. That just makes sense. But my buddy Sean found this really interesting case that is really stupid, and has things like this have led to a signed size value. Now this function returns size t, and it takes in a character string, another character string, and a number of one of its lengths, does something to it, blah blah blah. But the interesting thing that we realize is that when it returns, if an invalid character is encountered, it returns -1, but that's cast as size underscore t, so that's going to become unsigned integer max, which is a very, very large value. So if a developer was checking if this is -1 or some other thing, it may not work out the way they expected it, depending on how they cast things. So what came about is people wanted to be able to return error codes, and errors, usually -1 or some negative value, is returned in case of an error in general in C functions. And so size underscore t came about, and the valid range of values for that is -1 to size max, where size max is 32767. You don't have to remember that, but it's an interesting case. And the importance of all of this is that in certain cases in C programs and in libraries, these sort of bugs should be absolutely forbidden. They should not exist whatsoever, and one of the most prime examples are cryptography libraries. There's an excellent article from the Embedded in Academia blog in which the author investigates integer bugs in open source crypto libraries and finds bugs in almost every single library that he evaluates, with the exception of bcrypt and maybe another. And it's a very good read. So at some point I intend to explore whether or not these vulnerabilities, or bugs rather, exist in Bitcoin and cryptocurrency libraries, as those might yield interesting results. As this is the age of cryptocurrency heists, drones, and all sorts of other fun stuff that's right out of a cyberpunk novel. So another thing to note is that these are important to understand because a lot of developers don't understand these nuances, and sometimes when they're used wrong, they can lead to vulnerabilities. And suggested but not required reading on this material is a paper by the above author and others explaining integer overflows in C and C++. This should be helpful supplemental material, but not required. Now, floats are different than integers. They obviously have decimal values, and there's many nuances to using them. A float variable can be a special case called not a number, NaN. Another nuance is that you'll often find precision errors or bugs sometimes, and you'll see, if you've programmed a lot, you'll have seen this, where you add two simple decimal numbers and the result has some really weird trailing, almost infinitely small remainder on it that doesn't make any intuitive sense. Another nuance is that if you evaluate not a number equals not a number for all values, this is always going to return false. And that's a very interesting case with the C standard. Um, and you may see this in your homework. Also, the sums of many floats, just like above, the sums of a couple floats, the sums of many floats may not always add up right, and precision will get lost. And this is a pretty good guide to understanding floating points and these precision and nuance conditions, but it's not going to be tested material. Which brings us to the next subject, which is perhaps one of the harder subjects to understand. And we're going to cover a good bit of it, but not cover exploitation at this point. We're going to leave the actual hard exploitation of this stuff for the later lectures. And I want to highlight that this section in the Hacking Art of Exploitation book really covers this very well. And if you have any questions, you should consult this first, because it does do a superb job of discussing this material. So we're going to cover the problem with format strings and their misuse and some of their exploitation involving crashing a program and getting information links and disclosures, which are very, very important bug cases in this day and age. And they're used to defeat ASLR and enable ROP exploits. And we're going to discuss some of the mitigation techniques to secure formats string vulnerabilities and bugs. Basically involves preventing user input from being considered a format string. So the following functions use format strings in some form or another. We have printf, we have sprintf, we have snprintf, which takes in a number of bytes, and fprintf, syslog, etc. And so before we go any further, we're going to use Godbolt. I've just screen capped most of it to explore how functions are called. And this is compiled for 64-bit. And what we have is we're declaring this character buffer, and we're using sprintf to print into the buffer the following format string, and we have this integer value that we're using to print into it. So what's happening is that we're moving into RAX, the address on the stack of this character buffer, and then to EDX we're moving the first parameter for the format string that's going to get converted into there, and then we load into ESI the source index, the beginning of this string. And then we move the destination to the stack, variable here, buffer. We zero out EAX, I don't know why, and then we call sprintf. So let's look at this, altering it just a little bit with 64-bit, and see how this differs from 32-bit, which is on the next slide. So using multiple conversion specifiers, and we're just printing 1, 2, 3, 4, we'll see that this is actually, these values are getting pushed into registers. First one's going to be EDX, then ECX, R8D, and then R9D. And if we convert this to 32-bit, and you can do that with a 64-bit compiler by by entering the compiler flag -M32 to tell it the machine architecture is 32-bit. We'll get the following output, and you'll see how it's not moving it into like R9D or R8D or those other registers is in fact moving everything actually relative to ESP, which is a stack pointer. So it's pushing these arguments to sprintf on the stack. All right? And so if we take the previous example and keep pushing more and more conversion specifiers onto it, you'll find that actually after some point it will start pushing those arguments onto the stack in the 64-bit example. So depending on the architecture and depending on calling standard and depending on the type of function, the code on how functions are called will differ. So one of the most important things, as we just saw, is the architecture. There may be, for instance, more registers, more general purpose registers that make function calls more optimized, make them quicker. But also, depending on the compiler, for instance, Microsoft C compiler versus the GCC compiler, they have different calling standards. And this is important to consider, especially for reverse engineering, malware. If things are terribly obfuscated and happen to appear to be a valid exe and a valid ELF at the same time, I have an example of this later in the lecture. You might be able to pick apart what system it actually is by the calling standard if there's no easier way to do it. And also, the type of function will matter. System calls usually have their own calling standards that are independent of what the compiler likes to do. So, see how the format string function, when it's first being called, it's going to use the source index to iterate through that format string to find the conversion specifiers and then apply those values into them. So what dictates this behavior is this string itself. So that's going to be located at the source index if it's passed in the register, or it's going to be one of the first things on the stack for that function to use. So this is an example of a safe use of a format string where we provide the format string and we're printing in the given string to it. And this is an example of a format string vulnerability where that string specifier here is absent and we're just printfing the buffer. And many C programs actually do have this. And this is one of the cases that developers don't understand very well. And so remember how we just discussed that this is one of the first arguments on the stack that the function starts looking at. And so in this case, this is going to be one of the first things on the stack that the function starts looking at. And so if there are conversion specifiers present in it, which are the percent and then what follows it, whether it's D, U, O, X, F for float, E for scientific notation, C for char, S for string, and so on, it's going to look later on the stack or forward on the stack for those things. So the other ones to take note are %p prints out a pointer address, and %n doesn't print anything corresponding to a parameter, but it does print the number of characters written so far, which is interesting. So here are the various specifiers and the length that they take up. So the left column length here, these are length modifiers, and let me back up here. So the various things you can have are flags, width, a dot precision, a length modifier, and then the conversion specifier. And these are all the conversion specifiers. So the length modifier is this column. You can have nothing, the normal one, by default, HH, H, L, LL, and so on. But for now, let's just concern ourselves with this first row, and for each one of these values, it specifies this is the size that is going to specify. So let's go to this example, and say we take in a character string, and then we just do printf, and say that character string is %s, 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 and so on, so on, so on. Let's think about how this is going to behave. So printf, when it's called, is going to look at the string that's provided to it and look for conversion specifiers. And the first one it's going to see is going to read values off the stack as a pointer and dereference each pointer to start printing a string into, or printing a string into this buffer. And then the resulting buffer, when it's all done, perhaps gets printed to standard out or whatever it's been mapped to. So this will keep going until all the %s specifiers are satisfied, or until it segfaults. For instance, if a value on the stack that this reaches is all zeros, it's going to dereference a null pointer, which usually will cause a segfault, as we have discussed. So another thing to consider is printing out values on the stack, and this is for 8 bytes, and is going to print out the hex values on the stack, and it allows you to view the contents of the stack. Now we're not taking the values on the stack and treating them as pointers and dereferencing them and printing out the strings that arbitrarily may be laid throughout memory. What we're doing is we're sequentially iterating through the values on the stack relative to this point and printing out the values there. And so this is also going to print them out in little endian format, as x86-64 and x86-32 values are stored in little endian format in memory. So this is going to iteratively increase the argument pointer in that function by 8 each time. And the argument pointer is important for variable argument functions, and the most common case of those are format specifier or format string functions, and effectively also int main, which can take in an arbitrary amount of command line arguments. And you'll see that they're handled by va start and va list. Basically, va start is an argument pointer that starts at the list of the variable amount of arguments, and it gets iterated through and increased to exhaust through the end of the list. So va list is effectively an array, and doing this effectively is an argument pointer. So you can specify different widths. Here it would only increase the argument pointer by 4 after having read off this value. And typically you can only do this in increments of 4 or 8 bytes. I'm not sure on 64-bit systems. And this can be obviously exploited to view arbitrary memory values and locations. Now, it is possible to combine this with the %s case, where it takes a value on the stack, treats it as a pointer, dereferences, and goes to what it's pointing to and prints out the values there to view arbitrary memory locations. And so what we're going to do is we're going to use %x to move forward that argument pointer. Now this may be a little tricky, and if you have questions on this, you should read the section in the book. It's explained very well. It's going to use these chain of %x's, and I just have an arbitrary amount for this example, so it may not work right out of the box, to move forward that argument pointer. And now what you're doing is you're moving it forward such that when it gets to %s, it's going to point actually back onto the same string that you're using to look for the conversion specifiers, that is basically the format string. And then when you tell it %s, it's going to use, if you've aligned it right, the value that it sees as a pointer, dereference it, and then print out the value at that location. And so, since we haven't encountered this before, if you haven't seen this in C, the /x escape character actually denotes a special character. So in little endian format, we're specifying an address, and so the address is going to be actually not starting here, but it's going to be 04E5 F5 DE. And that's how values are stored in x86, 64, and 32-bit systems. And we're going to cover this way more in depth in the exploitation section, so you won't be expected to know this that much for the first midterm and for the first homeworks. But it's still important to know, and you'll be using it later in the class. So, format strings can also be exploited to write to a memory address. So for instance, that %n conversion specifier I talked about earlier actually will, instead of printing to the screen, will write into a corresponding parameter. So what this does is actually %n calculates the number of characters written so far. So 1, 2, 3, 4, 5, and then it finds the corresponding parameter and stores that value there. So this is going to write 5 to variable I. And that's a lesser known feature of format strings. So let's combine this with that previous example where I used the %s modifier with the trick of moving forward the argument pointer to, instead of reveal what's at that address, to write something to that address. So what we do here is push the argument pointer forwards until we get the %n modifier. And notice how if this is our buffer and the developer just has code that printfs it without any corresponding format specifier, and this is what we are providing, then when it gets to %n, hopefully in the exploit, it's been pushed forward that it's looking at this section and will use it as a function, well, use it as a pointer and store how many characters have been written so far to it. And so each one of these is a byte, and characters are a byte, so it's 1, 2, 3, 4, and then however many, depending on 64 or 32-bit systems, however many characters each one of these hex specifiers takes up, that length will be written into the address 04E5 F5 DE. Now you can use this in combination of other features like the width specifier. Instead of doing 08x or 04x, you can expand the value that's being printed to the screen to be 150 characters wide or n characters wide, however wide you'd like it. And this works well for writing small values, but in like 64-bit systems, it will not work well for writing a memory address. And this is where it gets complicated, and we're going to leave the tricky parts of this to the exploitation lectures. And oh, right, I should have had this slide before that. So we're going to explore the length modifier and show how for %n, this allows us to write to arbitrary memory, how these length modifiers actually change what we'll be writing. And so that's very interesting to consider, and something I leave for reference, as we'll likely need it for future homework. So the other modifiers are width and precision. And so, for instance, the following line will write a unsigned. It will take %u will map to 1, and it will expand it out to 0.0000000 blah 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 to 1, such that that's going to be 50 characters wide. And then write it to I, which is effectively going to be I equals 50, and so on. This will write 5,000 characters and store 5,000 in I. And in order to, there are multiple ways to write arbitrary values to arbitrary memory locations, but effectively, page 174 of The Art of Exploitation explains it best, and it has an example that effectively uses 4 writes to write just a byte at a time to take up all 4 bytes of a 32-bit address to pull off the arbitrary write, and the result stores DDCC at the corresponding address. However, you don't need to know this just for just now. As I said, we're going to cover this later. Which leads us to the last subject, concurrency and race conditions. So concurrency is a computational property in which several computations are executing simultaneously and are potentially interacting with each other. It's not always equal to multithreading, as multithreading involves a program that has 2 or more threads that may execute concurrently, then again, also may not. Parallelism, it really gets broken down into 2 different approaches, whether it's data-centric or task-centric. Data-centric parallelism really means that the data set is split into segments, and it allows the process to apply a function over each data segment in parallel. So you're doing chunks of it all at the same time. Task parallelism involves splitting the job into several distinct tasks that can be run in parallel. Now, this is perhaps cutting it a little short on this material, but there are 3 basic properties for race conditions that have to exist in order for a race condition to occur. First one is that there must be a concurrency property, or there must be some form of concurrency going on, and that at least 2 control flows must be executing at the same time in the process. The second property is that there must be some sort of shared object that is accessed by both or a number of those concurrent flows. And lastly, at least one of those control flows must alter the state of that object, that shared object. If they all share the same object but none of them change it, there will never be a race condition. However, say the front wheels and the back wheels share the rails, and also what shares the rails is the junction switch, and say the first set of wheels has passed the junction switch, but not the second. And then the junction switch kicks in, and then the process continues. And this is an excellent illustration of what can result from a race condition. You can effectively get a train wreck of a process that leads to a really messed up state. So, don't have any code to correspond to that, but the potential results from race conditions really involve corrupted values, can lead to elevated permissions or permission escalation vulnerabilities, and there are some notable CVEs that I've listed here, and also can lead to deadlocks, which can be used for denial of service style attacks, which have occurred in the past, although I did not provide any CVEs to refer to. So that is actually it for today's lecture, and the following is the required reading. Again, the format string exploitation section is a bit more difficult than the rest of the material, and section 350 does provide very good coverage of that. And that is all for today's lecture.